All right, so in this example, we're going to look at using Scikit-Learn to train and develop models using machine learning. Just as a note, we're not really going to look at any of the theoretical or conceptual components of machine learning. We cover that in other materials. Here, the goal is to just explain how to actually implement these algorithms within Scikit-Learn specifically. So it's really just how to do it in code as opposed to the concepts. All right, so just again, as normal, we'll start with our imports. So here I'm importing pandas and numpy as normal. Matplotlib, got my matplotlib in line there, so my plot in the notebook. And then I also have Seaborn for plotting. Some new stuff here is Rasterio. At the end of this, we're going to look at predicting to raster data, so geospatial raster data. So Rasterio allows you to read in raster data in Python, and then PySpatial ML allows you to predict to raster grids. Some of these things can be tricky to install into an environment, especially Rasterio and PySpatial ML. So they can be a little frustrating times. All right, and then from Scikit-Learn, which you can call them with sklearn here, I'm just pulling in certain things that I need. So the random forest classifier, the KNN classifier, the support vector machine classifier. I'm also bringing in grid search CV from the model selection module for doing hyperparameter tuning, and then a bunch of stuff from metrics for model assessment. And then from pre-processing, I'm bringing in the standard scaler, which is for rescaling data. Okay, so again, if you're in an environment, you should be able to that have all these packages or libraries available. You should be able to run this without error. Okay, so what we're actually going to try to do here is predict for a location on the landscape the likelihood that that location is a wetland based on terrain characteristics. So I've already developed training data in the form of CSV files, so basically tables. So let me read these in, and then we'll go ahead and just have a look at them. And then for the, okay. So, so anyway, basically the first column is the class. So it's either not means not wetland, and then wetland, and wet means wetland. And then the rest of the variables are different metrics related to the terrain, like the surface roughness, the surface curvature, the slope position, things like that. So you can see the shape here. So this is 23 columns. So the first column is the class, so that's what we'll predict. And then there's 22 other columns that we can use as predictor variables. And one of them we're not going to use the DEM column there. Okay, so that's the structure of the data. Now, the first step here is to split out the variable we want to predict, the dependent variable or the y variable, from the rest of the data set. So for the training data, I'm basically creating a train underscore y by just pulling out the class variable there. And that's just your standard pandas type syntax there. And then to get the x variables, I'm basically going to drop the class variable. And I'm also dropping the DEM variable, which is the elevation, because I don't want to use that as one of the predictor variables. So just the other 21 variables. And I do the same thing for the test. Now note here I provided two separate tables. One is training and one is testing. So these have already been split up into separate data sets. If you had one large data set, you would need to do some type of data partitioning, and there are tools available for doing that within Scikit-Learn. Okay, and then just to print those here, we basically have our column of the class and then our predictor variables. So we have that split up. Okay, so the next step here is we want to train a model, and most machine learning algorithms have some user-defined parameters. Generally, these things are termed hyperparameters. that can impact the results. So these are the things that the algorithm doesn't learn in the process of, the learning process from the training data. Instead, they have to be set by the user. And different algorithms are going to have different settings, different values that you can try. So generally, if you want to make sure you're getting the best model possible, you want to try to optimize the hyperparameters, right? So we're doing this using the grid search CV option here. So the first thing I do is create a dictionary where each of the properties here is something that I'm wanting to something I'm wanting to try to optimize, and then the associated values. So you can see there's a bunch of different settings here. And then what the grid search cross-validation actually does is it goes through and actually tries all these combinations and then determines which combination of hyperparameters give you the best result based on the cross-validation process. So anyway, this sets up the values we want to test. Then we initiate the model here with random forest classifier, no arguments, and then we do the grid search initiation. So we're going to use the random forest classifier. We're going to test these parameters here, and I'm doing 5-fold cross-validation. Note that 10-fold is generally more commonly used. I'm just using 5 here because it's a little faster, and then just some other arguments that are not super important for us. So anyway, that initiates it, and then to actually do the grid search to try to find the hyperparameters, we have to run the dot fit on that object. Now this can take a little bit of time because there's a lot of models it has to test because there's all these different combinations. So it has to go through 288 models. If you're really trying to be specific and you're using a lot of different testing a lot of different variables or values or whatnot, this can take a while. I've had optimizations take like over a day before if I'm testing a lot of things. So it's a little frustrating because it takes some time, but it is necessary. You might actually be able to hear my computer spinning up here as it cranks through all these models. While that's running, just a couple notes. Really, when you do this, you should anytime you run algorithms, especially if you want to compare different models or whatnot, you should optimize all of them separately, so it's a fair comparison. I'm not going to do that in the rest of this example, mainly because I don't want it to take forever to run. So I'm going to run this optimization just to show you how it works. And later on, we won't do that when we look at different feature spaces and different models, but if I was doing it for a real study, then I would do that optimization. And then I guess some other points. If you are using different algorithms, they're going to have different hyperparameters. Different models have different hyperparameters. And then there's different ranges of values or settings that are appropriate for those hyperparameters. So it does take a little bit of knowledge of the algorithm that you're trying to implement to actually set up a tuning process. Okay, so that's done. It didn't take too long. It's like a minute and a half there. Now if we run this, it'll tell us what settings it chose to be the best settings. So there's those settings. And then instead of actually just rerunning the model with these settings, you can just pull out the best model into a new object. So that's done with this dot best estimator. So anyway, this is saving that to a model or a variable called RF mod. So that's the final model trained with the best predictor or the best hyperparameters. Okay, and then once that model is saved out, we can use it to predict new data. So here I'm using it to predict back to the test data, so all of the trained variables from the test data set. So these are new samples that it hasn't seen before. All right, so if I run that, you can see it ran pretty quick. So you can see that it did use the settings that it shows. That just printing it gives you back the settings there, and then running the predictions on the test data was really fast. Yeah, anyway, so that's already done. And then once we have the predictions, we can use those to try to assess the model. So first thing I'm doing here is creating a confusion matrix. To do that, I feed in the correct class. So that's the test Y variable, so wetland or not wetland, and then the hard predictions, which we got here when we ran we predicted to the test X data with the model that had been trained. So if we run that, we get back. Oops, sorry, wrong one. If we run the confusion matrix there, we get back the confusion matrix. So this, these are the correct ones. These are the off diagonals are incorrect. So it actually looks pretty good. The classification report generates some metrics, generally for each class and overall, that are derived from the confusion matrix. Note you don't actually have to calculate the confusion matrix to do the classification report. You can just feed it the same variables, the correct class and the predicted class. So you can see here we have precision, recall, F1 score for both the not wetland and not wetland class, and then an overall accuracy here. Okay, so anyway, it looks pretty good. We've got like values generally above 95, 0.95. So it's looking pretty good. And here you can see like the samples. So we get 1,000 examples from each class, 2,000 examples total. Okay, there's another predict function. I guess it's a method technically. Predict method called predict_proba. And what that's used for is to get not the hard classification with the class probabilities. So if you use .predict on a model that's a classification model, you're generally going to get back the hard classification. If you're actually doing a regression model, which we're not doing here, then if you ran predict, you're going to get it back the estimated or predicted continuous variable. Now, with predict proba for classification process, instead of getting back the hard classification, that's going to give you back the class probabilities. So in this case, we have two classes, so we should get two probabilities that sum to 1, right? All right, so if we run that, that gives us back that. So let's have a look at it before we try to use it. Oh, actually, I guess I did that here. So this is showing the predicted probabilities for the wetland class, which is at the second index. If I swap this out for 0, then we get back the class probabilities for the not wetland class. And if we do them both, it should give us back, let's do that, should give us back all of them. Yeah, so again, these should sum out to a 1 at each position. Yeah, so as you can see, the results got spit basically out here basically in like a NumPy array. Okay, so once we have the probabilities, that we can do some other types of assessment. So what I'm doing in the next couple blocks here is creating a ROC curve, receiver operating characteristic curve, and calculating the area under the curve metric from it. So to do this, it generally wants the classes to be like indexes as opposed to like character strings. So what I'm doing here is I'm taking my test Y data, converting it into a NumPy array. Then I make a dictionary to map the class to a code, and then I apply that. So basically, what this does here is it converts all of the knots into zeros and wets into 1, and that becomes our new category. So the way this ROC AUC score function works is that it wants you to have the positive class be indexed as 1 and the negative class be indexed as 0. So basically we're just augmenting the data so that it fits into that framework. And if we run that, it spits back an AUC score. Generally anything above like 0.9 is considered good, like an A. It's like a grade scale. Above 0.9 is an A, above 0.8 is a B, so on and so forth. Okay, and then this actually plots the ROC curve using matplotlib. So I run this ROC curve function. Again, you feed it in the correct class and then the probabilities for the positive case. And then it produces a couple different outputs. So here we're getting the false positive rate and the true positive rate. And then we basically plot those. So plotting the false positive rate and the true positive rate there. And then changing some settings here of title, all that stuff. And if we run, we can see here now that we have an ROC curve. Cool. So anyway, that's one model. So let's just a quick summary of what we did. So basically, obviously read in or connected to all the libraries we needed, read in the data tables as pandas data frames, Had a look at our tables to make sure they seemed correct. Did some prep in terms of separating out the y variable from the x variables, dropping a column that we didn't need. Doing hyperparameter tuning using grid search and cross-validation. Pulling out the best model, using it to predict to the training data both hard classifications and probabilities, and then doing an assessment with a confusion matrix, confusion matrix based metrics such as precision recall and F1 score, and then the AUC, the area under the curve for the ROC curve, and then plotting the ROC curve. Okay, so now what I'm going to do is look at comparing different feature spaces. So we had 21 variables. So I wanted to know whether the model that used 21 variables is doing a better job than simply predicting the wetland occurrence using topographic slope, which is this variable. So slope underscore d is slope in degrees. And then a third model, we're just going to use slope in degrees and then the average slope position. So we're just going to compare these different feature spaces. So first thing I do is I do I split up the data so I just have the variables that I need. This I already did above, so I really don't need to do it again. So I'm just putting it here for the sake of completeness. Here, I'm just pulling out the slope d variable from the full set of variables. Note I have to wrap that inside of the data frame function here because since it's only one column, the default is to write it out to a pandas series, and I wanted it to be a data frame, so that just converts it from pandas series to a pandas data frame. And then here I'm just pulling out those two variables. So effectively we're creating new subsets of our predictor variables. Okay, and now I'm initiates three instances of the random forest classifier model, and I'm using 200 trees in the model. And then I fit it using the different sets of variables. So all the variables, this is effectively the model we had above, so really wouldn't need to do that again. Just slope, and then slope and slope position. Now again, for a fair comparison, we should do hyperparameter tuning for all these models separately. But I'm not going to do that here just for the sake of time, but if you wanted to do it, it'd be similar to how we worked up here, but you'd want to do each of them separately, and then get the best set of hyperparameters for each one. Okay, so anyway, we're just running one model, so these run really quick. Should just be like, a couple seconds there. So now once we have the model, so this is what we did above. So we're going to predict to the X data, and then get the classification report for each output. So here with everything, we had an overall accuracy around 0.96. We had an overall accuracy when we just used the slope was 0.86, so about a 10% drop in accuracy, and then the accuracy or the slope plus slope position was like 0.92. So yeah, generally, so it does look like we get some better performance if we include all these additional variables. So they must be providing some additional information that's not included in just simply the topographic slope. That's the idea. And then here's a comparison where we're doing it with the probabilities, right? So again, I'm doing the same thing here. I'm changing them from the not and wet labels into the 0 and 1 labels, and then predicting back the probabilities using each of the three models, and then from that getting back the AUC metric. So you can see with all the variables we're at 0.991, which just slope was 0.928 and slope position was 0.968, right? So we do see some improvement when we include the full set of variables. All right, cool. And then you can see just this here, I'm just printing back the probabilities. You can see you get the set for the, again, you get probabilities for non-wetland and wetland as two sets. Okay, and then here I'm making another ROC curve, but I'm plotting all three curves in the same plot space. So anyway, I get the data for all three curves. And then I basically add that data to the same plot, so there's all the same plot, but I give them different colors and different labels. And then I do some editing here for the plot, right, to clean up the margins and whatnot. So you can see there, yeah, again, so here the red there's our all variables model, and then slope plus slope position, and then the just slope model. Okay, so in that section, I compared different algorithms, or sorry, different feature spaces or different sets of input variables or predictor variables. So now in this section, what I'm going to do is compare different models, so or different algorithms. So we have the random forest algorithm that we've been playing around with, and we're now going to compare it to k-nearest neighbors and the support vector machine classifier. Okay, so in this section, I'm just going to use the slope d or the slope and the slope position variables. So I'm just going to predict with those two. So one thing that is important for certain classifiers is that some classifiers are sensitive to data being on different scales, and it turns out that all the predictor variables we have here are actually measured on different scales, which is an issue. So if we're going to use support vector machines and k-nearest neighbor, which are sensitive to the differences in scales, we actually need to get all the data in the same scale. So that's what this standard scale function does. So we initiate this scalar. Then we fit it to the train X sub data. So it's basically going to determine how to rescale the slope and slope position variables. And then once we've trained that model, we run a fit on once we train the model or fit the model, we use it to transform the variables into a common scale, which I believe is -1 to 1. And then we also apply that same thing to the test data. So note that the transformation is just based on the training data, but then we apply it to both the training data and the test data. And that's because we don't want the algorithm to see any representation of the test data. So if we'd include those in the statistics used to do the transformation, that's a bit of a data leak. So this is commonly how you do it. You get the transformation on the training data, but apply it to the test data also. So anyway, that's what this is doing. It's just rescaling the variables for us so they're consistent. I guess like a -1 to 1 scale for each one. So here's the original values here, and then here's the rescaled values. Pardon me. Okay, and then we initiate our models. So I'm initiating a random forest classifier with 200 trees, a k-nearest neighbor classifier with looking at the 7 nearest neighbors, and then the support vector machine classifier with the default hyperparameters. And then we fit those using the training data and with the rescaled. Now note, random forest, you wouldn't have to use the rescaled data for that because it's not sensitive to scale, but I did in this case just for consistency. And then there's our y variable that we're predicting. Again, it would make more sense, or it'd be more robust if we did hyperparameter tuning on all these models separately. That's a fair comparison, but again, I'm not doing that here just for the sake of time. But I again showed you above how you can do hyperparameter optimization with the grid search and cross validation. Okay, so anyway, this initiates the models and then trains them. And again, this isn't a very large data set, so that works pretty quickly. Then once we have the models, we can use it to predict to the new withheld test data and then get it back our classification reports. Okay, so these all are actually pretty similar. The overall axes are all 92. Pardon me. Again, this is just looking at the ROC curves, nothing new there. So they're all 0.96, something slightly different, but not very different, and again plotting the ROC curves for all three models. So as you can see, like kind of summary is that the feature space did make a difference. Using all the variables generally was a better model than using just slope or just slope and slope position, but these three algorithms for this specific problem actually perform fairly similarly. So that's not always going to be the case. It's a case specific issue, but in this case that was the result. All right, so in this last section, I just wanted to show you how you can use a trained model and predict back to a geospatial raster grid if you want to get like a map output. And this makes use of Rasterio and the PySpatial ML libraries. So as I mentioned above, these things can be tricky and frustrating to get installed into an environment without like dependency issues. So just fair warning with that. Okay, so anyway, this file is basically a stack of all the predictor variables. So each of the bands or layers in the raster represent one of the predictor variables. So at each pixel, then you have all the x variables, and thus you could predict back on a pixel by pixel basis, and then get back a map output. So this pml.raster is using the Pi Spatial ML library to read in this file that's in image format. And then here I'm just listing the band names. So if I run that, you can see here that it comes in with default band names. So it's the name of the file underscore and then the number. So 1 through 21 there. You can see there's 21 predictor variables. Now in order to run the model and use this data, we need to make sure that the names are the same, right? So, and that they're matched up correctly. So I know you have to know the order of the bands up front. So make sure if you do this type of process, if you stack like a series of predictor variables into a multi-band raster, you need to know which band represents which variable. So I'm using this .rename function, so I guess method, applied to a raster to rename the bands. So the original name and then the new name. And again, they have to make sure that they match up correctly. Yeah. And then again, this is just defined here as a dictionary. So this should rename the bands, and I'm just saving that to a new copy. And I'm just printing the names here to make sure. It looks like they're fine. Good. And then now I'm applying the model to predict to the raster now instead of back to just a table. So to do that, it's the raster object, and then the .predictProba method, and then the estimator is the name of the model. So I'm using my random forest model there, and that's going to get saved to this results object. Okay, so I'm running that. Now, this can take a little bit of time, especially if you, especially if you have like a really large raster, just a lot of predictors, or a small pixel size or whatever. And I've had to troubleshoot this a lot. There's sometimes just some issues with it. So anyway. It can be frustrating, but it is a good way to try to predict back to a raster stack. I'm not sure why I'm getting this message, because I changed the band names, which seems to be what it's indicating is the issue there. If it doesn't work, I'll have an older version I can read in, just to look at the output. That may be an issue with like a dependency or something on my end. I'm not sure. Okay, well, hopefully this finishes up. Just while that's finishing up, I'm just going to explain the rest of the code here. So this result.write, that's used to write out a raster to disk, and this is specifically like a geospatial raster, so it should have like georeference information and stuff still associated with it. And then once I write it out, I read it back in. So I used rio.open. So that's this is a function from the rasterio package. And then I pull out the band that I want. So it's going to produce a stack where the first layer is the not wetland probability, and the second layer is the wetland probability. Now, the way rasterio works is it actually doesn't index starting at 0 when you're dealing with bands. So band 1 is band 1 and band 2 is band 2. And then just setting up some parameters here for the figure, and then I'm plotting it. So whenever this reads in, it basically reads into like a NumPy array. I'm just applying a stretch and setting a high and low value. Since this is a probability, they're scaled from 0 to 1, so I kind of know that already. And this is still running. Give it a second. I thought this would run quicker than this, but I guess it's wrong. Oh, looks like it's done. That's 2.5 minutes. That's not too bad. All right, so I'm going to change this to 3 because I already saved it, and run it there. All right, and that should have wrote that layer out. You can see here that has 2 layers. You have a probability for each one, the number of rows and columns, the resolution. It's a 9 by 9 meter cell size. And then the values there. And then I just need to change this to 3 to match, and then read it in. There we go. So I don't know why I got this error, because the output looks correct. I'm not sure. But anyway, this is the output. So basically the darker blues indicate higher likelihood of wetland occurrence, and the lighter areas are less likelihood based on the model. And this kind of makes sense. It's a lot of the low areas and flat areas and valley bottoms that have higher probability. Yeah. Okay. So anyway, that's quick example of doing some machine learning using Scikit-Learn, and then predicting back to a raster stack if you're working with spatial data.